Hey, what's up, guys? Okay, so in this video, that I will describe another topic. Basically, it's also related to the quadratic reciprocity, and this is another way to prove it. But this will open a completely new world this will open a completely new world in the number theory. Okay, so I want to talk about the quadratic Gauss sum. Okay, now this can connect it to the very deep mathematics, but in this video, let's just talk about the definition and the start from this quadratic Gauss sum and the proof. Okay, so basically, I want to say that I want to use this to prove the reciprocity rule. Reciprocity. So basically, we want to prove that QP is -1, P -1, Q -1 divided by 4. Okay. So before we give a definition, let's consider P is R prime. And then let's say omega is the P roots of unity. Okay. So let's talk about some lemma. Okay, so first lemma is very simple. Just if you go to omega AT, that you get T, if you start from T to P -1, that is 0. If A is not 0 mod P. So basically, if A is not multiple of P, then this guy will be 0. Okay, so you can prove by this. Oh, it's very trivial. You prove by yourself. But the idea is that you use the geometric series, right? So this is just 1 minus omega A, and then 1 minus omega A to the P. Okay, so if omega A is not 1, then this guy is 0p, right? Because omega P is 1. Okay. So if A is not multiple of P, then you will get 0. If A is 0 mod P, then each guy will be 1, right? You will get P. Okay, so let me just collect the results. So let me just write it as this way. Okay, so let me just write it as this. So it's P, and if P divides A, else 0. Okay, so this also gives you a fact, which is simple. You can like 1 over P omega A x minus y. If you've ground let's say T, sorry, T, and the T from 0 to P minus 1 will be this, right? So this will give you the, let's say, delta xy. Okay, so delta xy definition is just the 1 if x is y mod P. Basically, you just change this A to be x minus y and else. Okay, and there is a lemma 2. Also, lemma 2 is simple, right? Lemma 2 just say that if you do the AP from A from 0 to P minus 1, you'll get 0. Okay, so basically this is simple, right? As I said that since you know the format, you know that format, where is this A, right? It's mod P. This is the Fermat's-Little theorem, and the Fermat-Little theorem tells you that the number. So there, if you do this, right, you can prove the following. Right? You prove that AP minus 1 divided by 2, mod P, right, is either plus or minus 1. Okay, so this equation can be factorized in this way. And so this is P minus 1, right? So there, right, so total we have P of Lem, and the half, right, half of it is minus plus 1, half of it is minus 1. So it's 0. Okay. Okay, so now we can go from our beautiful definition. This is Gauss sum, which is really weird. We divide the GA to be summation of TP omega AT. T from 0 to P minus 1. This is called the quadratic Gauss sum. Okay, and you might heard of some people say that this is similar to gamma function. And you might say what the right is doesn't make sense, right? Because if you heard about a gamma function, it looks like this. If you know about most on engineer mathematics or some mathematical physics or whatever, right, you know this definition of gamma function, right? But it looks like, right, why these two are why these two are like similar. Okay, so let me just provide intuition. So this guy, right, since it is 0 to infinity in a finite field, right, we should add like this. So this is possible. And for this one, this guy, right, should match with this one. Okay, reason is that this guy is multiplicative, right? Not multiplicative, but looks like this. Okay, and this guy also have this property, right? If you like a t1, a t2, then you get omega a t1 plus t2. Okay, so these are two similarity. And for this one, that you can say it's the same as this one because this one has property that t1, t2, z minus 1, z minus 1 will be t1, t2, z minus 1. Okay, and for this one that you can easily, since it's multiplicative, so t1 p, t2 p will be t1, t2 p. Okay, so you can say that this guy has the similar property of all these function. You combine with such two function as its property, and I combine with it in the finite field, then I define the Gauss sum. Okay, the amazing thing is that you can use this to prove quadratic reciprocity. What the hell, right? Why someone can come out with this? Okay, so this is very deep. Okay, and the theorem, and this theorem is simple as a GA, right? It's omega AT, AP, T from 0 to P minus 1 is actually APG1. Okay, so if you shift it from A, that becomes G1. Okay, G1 is just, so G1 just you put A to be 1. And G1 is a weird object, so we will see it. Okay, so proof is very simple. The proof goes this way. If A is 0 not P, then we know that omega AT is 1 for all T, right? So in this case, that GA will just be right, since A, right, so it will just be sorry, this is T, will be TP, right? And since it's 1, right, so it's T from 0 to P minus 1, then it's 0. Okay, and okay, so this means that if A is 0, 1, P, then this is 0, and you can obviously G1 is 0, this is G1. Okay, so sorry, not this. Let me just, so G1, right, by definition, G1 is just XP, right, omega X. X from 0 to P minus 1. Okay, but what I'm saying is that if A is 0 mod P, then G is 0, so that means that this term is by definition 0, right? So for A equals to 0 mod P, then this equation is true. Okay, so I only need to consider that the A is not divisible by P, so I only need to consider this case. And now it's just very simple. Let's say I use this times GA, so I get the omega AT, ATP, right? Notice that this Legendre symbol is multiplicative, and so I have this. Now, using some group theory or stupid theory, you know that AT is just permutation of AT. Sorry, the AT as a set is just a permutation of the 1, 0 to P minus 1, right? So I can make a change of variable. I say this is X, this is just X, and then XP. Then I get G1, right? And so I get AP, GA is G1. But this guy is either plus or minus, so I can get GA just AP, G1. Okay, so until from now on, okay, I will use G1 to be used G. Okay, just for the simplicity. Okay, and another theorem, which is also weird, is that G squared is minus 1, P minus 1 divided by 2, and P. Okay, so for this one, that the difficult in the one like tool in analytic number theory is compute this G explicitly. So this guy can be computed, but it's very weird. It's very difficult. It's tedious. Okay, but G squared can be easily computed. Okay, So I'm making remarks that G is hard to compute. So I will talk in a future video, but it's tedious. But G squared can be computed easy. Okay, so let's do this calculation. And okay, hopefully it's not difficult for you. Let's see. Okay, the first one that I want to say is that you can define a GA, negative GA, to AP, negative AP, and G squared, right? By my previous notate, by previous lemma, right? So this tell me that GA, G negative A, can be like, I can, since multiplicative, right? So I can collect -1 to P and A squared, P, G squared. And right, but this guy is also possible. This guy is also what, always what, right? So because this guy can written as APX squared. So it's just, so we have this. Okay, so we have the, yeah, just from one side. Okay. Okay, so this means that if I go summation GA, G negative A from like 0 to P minus 1, then I will get the same thing. I will get -1P and the G squared, and I get P minus 1 term. Okay, because yeah, when A, yeah, it looks like we should got what? We should got the P term, right? But if A is 0, then this guy is 0, right? So I should, so since A is not divisible by P. Okay, so if A is divisible by P, then it's 0, right? So we only got P minus 1 term. Okay, and okay, yeah, so this is one way. And there's a second way to compute it. A little bit tedious, but let me just quickly go through it. So you have GA and GA. And by definition, right, you can write as XP, right, omega AX by definition, and YP, omega AY. So let's say X is from 0 to P minus 1, and Y is from 0 to P minus 1. This is negative. And now I can compute. I can get X equals 0, P minus 1, Y equals 0, P minus 1, and that do the same thing to a permutation. Like that. Sorry, I don't do anything. I just multiply it. Okay, and if I get, now I get start from A from 0 to P minus 1. I get A from 0 to P minus 1. When I do this, okay, so now this I can just easily compute. Probably not easy, but basically I can just swap this into this, right? So I get X equals to 0, P minus 1. I have Y from 0, P minus 1, XP, YP, summation A from 0 to P minus 1, omega A X minus Y. So this is delta XY. P, right, as using my previous lemma. Okay, so it means that Y must equal to X. So I get X equals 0, P minus 1, XP squared, P, delta P. Okay, so there's no delta here. Okay, so now it's very simple. Now this guy is always 1, right? So I get P times P minus 1. Okay, because if X is now, if X 0, then it's 0, right? Okay, so that means this guy is P minus 1, P minus 1. Okay, so we got what? We got G squared is -1P and P. Okay, then by definition, this guy is just by Legendre, by Euler Criterion, this guy just this. Because this guy, remember the Legendre symbol is either plus or minus 1. Okay, so prove our results. Okay, and what I want to say is that, okay, so now we have this tool, so we can prove the very real results, right? We can prove that basically we can show the quadratic, the reciprocity law by the previous results. By the previous real result G squared, right? Simply prove that G squared is just -1 PP. Okay, Okay, so now let's compute. So I consider P, Q are odd prime. So let's do G square and for power like Q. Okay, so let's do G to the Q. Okay, so G to the Q is simple. What is it? G to the Q minus one is simple, right? Because I can do like G square Q minus one. Then I get the notation looks very confusing. Okay, so this is G and this is Q. Okay. Okay, so I will get the let's write as this. And for the convenience, let's using this to be P star. Okay, just for the convenience. So this guy I can write as P star, right? I have P star equals to Q minus 1 divided by 2. Sorry, P star times Q minus 1 divided by 2. Then I get P star. By definition, I get, right? This is P star Q. Q, right? I mark Q. Okay, so this now I use mark Q. Okay. Okay, so notice that this P star is a number, right? So this is well defined. Mark Q, right? Well defined. Okay. Okay, so okay, so this show that G to the Q will be P star Q and G Q. This is G to the Q. Very bad notation. Sorry about this. G to the Q is P star Q GQ. Okay, shit. Very difficult. Okay, so when I type Q, when I say this mark Q, then I'm not because Q, right? Q is not non-integer, right? So this you should view this as the Z to the Q with the roots of unity. I mean, in terms of P. Yeah. So this is the ring. Okay, some commutative ring. Okay, some algebra integer. Okay, but it's fine. That doesn't matter. Uh, okay. Okay, so let's preserve this. Okay. Okay, so on the other hand, I can just using our previous results, right? Because G to Q, I can write as TP omega T, right? And using T from 0 to P minus 1, numeric definition, and I using Q, and I doing this mark Q, right? So I can just I can just collect a Q and omega TQ and T from P minus 1, right? Since I doing the mark Q word, and this guy, right? This guy just, so this is mark Q word, and this guy just TP, right? So I can, because Q is odd, right? Q is odd. Right, so this TPQ will be just same as this T0 P minus 1. And this guy, right? This guy just write down. Okay, so this is just, by definition, this is just what? This is just my previous definition called GQP. Okay, so what I have shown is that the QPG, as I previously QPG, is the same as this guy, right? This guy is the same as this guy in Ma P. So I got GQP. Okay, so this is Ma Q word. Okay, but okay, so let's say you get QPG. And now this guy, right? This guy, by our previous lemma, right? So we got stupid lemma say that you can pull out this Q. Okay. You can pull out this Q. Oh, sorry. We prove this. So we'll yeah, we want to use this, right? So we got P star Q. So we got P star Q G mod Q. Okay. And okay, so now I get this. Okay, so let's multiple g's, so we got this, right? So we can like do g squared. So let's do g squared. Okay, so always mark q. And so g squared is what? G squared is p star, right? So we get qp p star equals to p star q p star mark q. Okay, and but p star is a number, right? P star is just minus one, p minus one divided by p star just this. And this guy's dv is corresponding to q, right? So I can just neglect it. Okay. But finally, these two numbers are in plus or minus one, right? So I can neglect this mark q. Okay, so let me just write down. So finally, we get qp. Oh, finally, we neglect this stupid term. Okay, so we have this. Okay, so this guy is just p, right? P is minus one, p star is just minus one p divided by two p. Okay, so since it's multiplicative, so I can write it as minus one q p minus one divided by two and pq. Okay, now from the previous reason, the lemma, right? There's a lemma. So what? Okay, so you get this, right? You get this. So what should we do? You use what? You use definition, right? Minus q minus one q, just q. Sorry, you just remember this q minus one divided by two, right? So this is Euler Criterion. So you get minus one q minus one divided by two, and the p minus one divided by two, and the pq. Okay, so you can multiply this pq to the left hand side. So you get qp pq. Since it's plus or minus one, so you don't care about it. You can just multiply into it. You get minus one q minus one divided by two, and the p minus one divided by two. Okay, so this strange, and very weird Gauss sum calculation that you can algebraically prove the Legendre symbol using the Gauss sum. So it's very weird that this is true, right? So weird. Why someone can come out with this like weird function, right? Which give you something. It is very deep results that it's very deep results. So it's not simple to see that why someone can come out with this number, this definition. Okay, so see you guys in the next videos.